Chapter 10, Lesson 2. So in this lesson we'll talk about the gas laws, the common gas laws associated with gases. And these are the four parameters that we'll be dealing with. Temperature. We defined temperature a little bit last time. We also defined pressure, worked with it. A volume should be familiar to you as the amount of space occupied by the gas. And N, recall, is moles, or the amount of gas that we have. Amount in terms of how many molecules, say, of the gas. The first law we'll talk about is Boyles Law. Mr. Boyle was a very famous scientist who experimented with many substances and found a relationship between pressure and volume. So Mr. Boyle's law is relating pressure and volume. And in general, what this law states is that the two are inversely proportional, which means if pressure goes up, then volume must go down by the same amount. Or conversely, if the pressure goes down, the volume increases by the same amount. This can be seen with this little experiment using a manometer. So here we have a volume of 60 milliliters with atmospheric pressure, which is, we'll say atmospheric pressure is 760 millimeters of mercury. We'll say it's standard, and notice how the two lines are actually on the same level. Meaning that the volume of the gas, or the pressure of the gas, is 760. So volume of 60 mil, 760 torrs. And once we've added another, essentially what we've done is we've poured another 760 millimeters worth of pressure. We've doubled the pressure effectively. And as you double the pressure, the volume, notice, goes down to 30. So you've doubled the pressure, and then you've halved the volume. This is just a fancy way of showing that as pressure goes up, volume goes down. Now let's take a look at an equation that represents this. It's a good idea to be able to represent this mathematically using an equation. Pardon me. And the equation says P times V equals K. Now this is how we represent an inverse relationship in mathematics. Another way of doing it is this way. If you rearrange the equation to solve for volume, you'd have to divide by P on this side, you divide by P on this side, and effectively you've got 1 over P times K. What this equation means, actually you can see from the equation itself, that K is a constant. This number does not change. So as pressure goes up, the volume must go down to counterbalance the increase in pressure to keep the K a constant. That's the idea. Now anytime you plot an inverse relationship, what you see is this sort of graph. And this is counterintuitive because you would think that an inverse relationship should kind of look like this with the negative slope, but it is not. In fact, if you take a look at this graph, say at 1 of pressure we have 1 volume. If we double the pressure to 2, we're going to go from 1 to 2, notice what happens. The volume halves, 2.5. So 1 and 1, and then 2 and 0.5. You have to have this curve-like graph to represent an inverse relationship. And actually, if you're in math, your y equals 1 over x graph looks exactly like this. This essentially is y equals 1 over x. What you could do is you could straighten the graph out by plotting the inverse of P, by taking all your pressures and inverting them, and then you'll actually get a straight line. This is a little trick that we do in math to essentially get us a straight line, and the reason we do this is then because we can get the slope, and the slope of the line is usually your constant. That's how we would determine K. We're not going to do much with this. This is just an overview. We will be eventually doing this sort of math in another chapter later down the road. The second law we'll take a look at is Charles' Law. Charles' Law deals with volume and temperature, and this is a directly proportional relationship, which means as temperature goes up, volume likewise goes up, or as temperature decreases, volume decreases. And you can see this is mathematically, the relationship says V over T equals a constant. This again means if volume increases, the temperature must increase by the same amount to keep K a constant. Alternatively, you can write it as V equals K times T by just multiplying T on this side and multiplying T out on this side is the idea. And this is technically your y equals whatever x, k would be the slope, y equals mx version of the graph. And this gives you a positive slope. This does give you a straight line with a positive slope. And these are experimental conditions or experimental measurements of the volume of a gas based on its temperature. Now, Charles' law was actually used to determine the absolute zero of temperature. This is famously what they did essentially is they graphed a bunch of temperatures and volumes at at reachable or at standard temperatures, the ones that they had access to, and then they extrapolated the straight line to the zero volume region, and they found negative 273. You can actually verify. There are some experiments you can do in the laboratory to verify absolute zero, which is pretty neat. And here, yep, so we have a straight line. Avogadro's law is the third one we'll talk about. Avogadro's law is also directly proportional, which means now Avogadro's law deals with volume in moles. So as volume goes up, so does moles. Or it's better said that as moles goes up, so does volume. This simply means as you increase how much gas you have, the amount of volume increases. Now this is assuming that everything else stays constant. In all of these cases, we actually assumed that all the other parameters stayed constant. So in this case, temperature and pressure are constant, is the idea. And then this will work pretty neat. And again, if you were to graph this, because it's a direct relationship, you'd get a straight line if you do moles versus volume. Okay, why don't we do a few problems with this idea. The first problem states the following. We have a balloon with a volume of 450 liters, 4.50, where the atmospheric pressure is 748 torricellis. If the temperature remains constant, what will be the new volume at a pressure of 557 torr? So the pressure went down. We're asking what will be the new volume. Now, just looking from a distance, based on our laws, the pressure and volume are from Boyles Law, and pressure and volume are inversely related. So if pressure goes down, the law says that volume goes up. So we should see a higher volume of our balloon. Now there are a few ways to solve this problem, and I will show you what's called the ratio method. And if you took me for Chem 1, you will recall this ratio method. Essentially, this uses simple mathematics to relate the two variables, essentially. And the way we did it is we would list the two variables that are given to us. So in this case, we're given volume, and we're given pressure. And then we list the initial volume, V1, final volume, V2, initial pressure, P1, and final pressure, P2. So we list these values, and then we use them to do the problem. So let's go ahead and take red here. So our initial volume is 4.50, this would be liters. Our initial pressure is 748 torricellis. Our final volume is our unknown, so we'll stick a question mark here. Our final pressure is 557 torr. So this is essentially a way to keep account of our variables. And then we'll begin with our volume, and we'll allow the pressure to increase or decrease the volume based on the relationship between the two variables. So essentially you're beginning with your unknown. So in this case, 4.50 liters, and then we multiply by a ratio. This is where the ratio method comes in. We'll multiply by the ratio of the pressures. And the question is, which one of these two pressures would go on the top, which one would go on the bottom? According to our relationship, as pressure goes down, in this case we see that our pressure is going down, the volume must go up. So to make the volume go up, we have to put the bigger number on top, 748 torr, and the smaller number on the bottom. And this will ensure that in the end our volume gets pulled up as is predicted by Boyles Law. So you'll plug in 450 multiplied by 748 divided by 557. And you should get yourself a Oops, let's try that again. 450 times 748 divided by 557, little glitch. We should get ourselves 6.04 for the value here, and liters, because the Torricelli is cancelled out. 3 sig figs, 6.04 liters for the final volume. And as predicted, our liters, our volume did go up. So we'll keep it at this. Let's try another example, a similar example. We have a balloon at a temperature of 24 degrees Celsius and a volume of 2 liters. We are going to take the balloon outdoors where the temperature is 12 degrees Celsius. So here we're dealing with Celsius, which is temperature, and liters, which is volume. So our relationship is Charles' Law. Charles' Law gives us the relationship. Charles' Law. And Charles' Law simply says if you increase the temperature, think you're allowing the molecules to move faster, and as the molecules move faster, they spread out. So the volume of the gas increases. So let's go ahead and use the ratio method again, take an accounting of our temperatures and our volumes. So we'll do V1, V2, and then we'll do T1 and T2. Let's go ahead and list our variables. It looks like our initial volume is 2.00 liters. It says what will the volume be outdoors. We don't know the volume. Our initial temperature is 24 degrees C. Our final temperature is 12 degrees C. So as we've done before, let's go ahead and begin with our unknown. So we got that's volume. So we got 2.00 liters. We'll multiply by the pressure, by the ratio of the temperatures. And it looks like our temperatures went down. And if our temperature goes down, according to Charles' Law, so will our volume. So in order to make this work, then for volume to go down, we must put the small number on top, the big number on the bottom. So what you'll do is 12 is our small number and 24 is our big number. However, we cannot put 12 and 24 in the equation because these are not absolute temperatures. We have to convert both of them to Kelvin. So in fact, this has to be amended to plus 273 for both of these, plus 273, and we get ourselves 297 Kelvin, and then here we have ourselves 285 Kelvin. You have to use Kelvin. In fact, if you don't, what it looks like is it looks like your temperature was halved, cut in half. And 24 is a pretty decent, pretty comfortable room temperature. 12 outside, it's a nice, a stable fall day, 12. So you don't expect your volume of the balloon to go down by half because the temperature did not really drop by half. It dropped just a little bit based on the Kelvin. So we'll have to use the Kelvin values. But again, since we needed to go down, since the temperatures went down, Charles' Law says that volume will go down. So we'll put the small number on the bottom, small number on top, big number on the bottom, to ensure that this ratio pulls the liters down. So we'll do 200 times 285 divided by 297, giving us a fine value of 1.92 if we use significant figures, liters. So notice the liters did go down as predicted, but not by half. It went down by a little bit. Enough, probably be unnoticeable. A 2-liter balloon will probably, you won't notice that it went down by that much. So this is, again, applying the same idea. Don't forget, your temperatures must be in Kelvin. We can also combine in the previous two examples, we've combined two of these, pressure, volume, and volume and temperature. But we can combine 3 of them together, including moles, and do a gas law problem in a combination. I think this is what our last example will show us. So our last example, as you'll see, has 3 parameters that we'll work with. We have an inflated balloon with a volume of 6 liters at sea level, which means we're at 1 atmosphere, and it's allowed to ascend until the pressure is 0.45. The higher you go up in the upper atmosphere, the lower the pressure. This is because the air is rarer, less molecules, therefore less pressure. And then during this ascent, the temperature went from 22 degrees C down to negative 21. The higher you go, the colder it is. You may know this from if you've ever taken a plane, even in the middle of the summer, and they'll announce that on the outside of the plane the temperature is pretty chilly. They'll usually say some kind of negative Fahrenheit temperature. So looks like our balloon will suffer a decrease in pressure and a decrease in temperature. Okay, let's go ahead and use the ratio method again. Let's keep account of the three variables that we have. We have volume, we have pressure, and we have temperature. Let's set this up as V1, V2, P1, P2, and T1, T2. Let's go ahead and account for our variables, fill them all in. In this case, we have ourselves 6.0 liters as our initial volume. Here it says calculate the volume of the balloon at the final altitude, so this will be our unknown again. The pressure, initial pressure, is 100 atmosphere, and the final pressure looks like 0.45 atmosphere. Initial temp is 22 degrees C, and final temp is negative 21 degrees C. Recall that we have to convert our temperatures into Kelvin, so we're going to add 273, and this gives us 295 Kelvin, and this gives us, if we subtract 21 from 273, technically we get ourselves 262. 252, I'm sorry. 252 Kelvin for temperatures. And then again, let's begin with volume, or unknown. So we'll do 6.0 liters. In this case, we'll multiply by 2 ratios, because 2 factors are causing the volume to go up or down, or affecting the volume. And the first one, let's go ahead and put the pressure ratio. And now, because our pressure is going down, based on Boyles Law, as pressure goes down, volume, we know, must go up. So we'll put the big number on top. So we'll put 100 on top and 0.45 on the bottom. And next, our temperatures will essentially affect it in this ratio. Looks like our temperature is also going down based on Charles' law. If the temperature goes down, the volume will also go down. So our volume, to make it go down, we must put the small number on top. So we'll put 252 on top and 295 on the bottom. So effectively what this is doing is the pressure component is actually pulling the volume up, and the temperature component is pulling the volume down. And whichever one is bigger will determine the final volume. So if you do this calculation, go ahead and try it. 6.0 times 1 divided by 0.45 times 252 divided by 295. And you get yourself 11.4. So essentially, since we have 2 sig figs, 11.4, we'll say we got ourselves 11 liters. So our balloon almost doubles in size, and this is actually to be expected because the pressure went down significantly, whereas the temperature went down, but not as significantly. So your balloon has doubled in size. So you've let that little balloon go at the sea level, and as it ascends higher and higher and higher, it expands. So the balloon is bigger, and as it ascends higher and higher and higher, eventually the balloon, we'll say here it is, pops. So eventually you get itself a little boom, and the balloon is gone. And then that little piece of a balloon just comes right back down. So unknowingly you've sent your balloon to its death. Every time you release a balloon, it gets high enough, increases in volume, and bursts. Okay, and this will conclude our second lesson of Chapter 10.